The universe is a silent ocean of stars. We gaze into a cosmos filled with hundreds of billions of galaxies, each brimming with the raw ingredients for life, and yet we hear nothing. This is the heart of the famous Fermi Paradox. Where is everybody? Today we will journey through the most compelling scientific and philosophical answers to this profound mystery. You will discover the leading theories explaining the great cosmic silence, from the possibility that intelligent life is incredibly rare to the chance that it is simply too alien for us to recognize. We will explore if we are alone, if we are being ignored, or if the universe itself is working against the rise of civilizations. What does this vast and quiet cosmos make you wonder about our own place within it? Our world floats in a cosmic sea of unimaginable scale, a single, fragile drop in an endless dark ocean. This is not just poetic imagery, it is the stark reality of our situation. Consider our own galaxy, the Milky Way. It is home to over 100 billion stars, many of which are likely orbited by planets. Now, expand your view to the entire observable universe, a realm containing not billions, but trillions of galaxies. The numbers are so large they defy human comprehension. This sheer scale is the first and perhaps most formidable barrier in our search for others. The distances between stars are not just large, they are monstrously vast. Our very nearest stellar neighbor, the Alpha Centauri system, is over 4 light-years away. This means that even a beam of light, the fastest thing in the universe, would take more than 4 years to carry a simple hello to that system. A conversation with a reply taking another 4 years becomes a dialogue spanning generations. Now, consider that most stars are thousands or even tens of thousands of light-years apart. A civilization could be broadcasting powerful signals from a star 1,000 light-years away, and by the time those signals reached us, the society that sent them could have risen, flourished, and vanished into history. Astronomers point out that our search for signals has so far been like scooping a single glass of water from the Pacific and declaring the ocean empty of fish. We have only sampled a minuscule fraction of the cosmic ocean, both in space and across the deep river of time. This humbling realization about the sheer size and age of everything reframes the entire question. The silence we hear may not be a sign of absence, but a simple consequence of distance and time, setting the stage for the next layer of this profound mystery. Amidst this vast and silent cosmos, one man decided to give structure to our wonder. In 1961, astronomer Frank Drake gathered a small group of scientists for a secret meeting. Their goal was not to find an answer, but to frame the question itself. The result was a deceptively simple formula now known as the Drake equation. It was not built to give a single number, but to break down the grand mystery of alien life into a series of smaller, more manageable questions. The equation multiplies together a chain of probabilities. It begins with the rate at which new stars form in our galaxy. Then it asks what fraction of those stars have planets. Of those planets, how many are in the habitable zone where conditions might be right for life? Next comes the leap from chemistry to biology, the fraction where life actually emerges. Then the leap to intelligence, where life becomes self-aware and curious. After that, the fraction that developed technology capable of broadcasting their existence into space. And finally, the most haunting variable of all, the length of time such a civilization lasts before vanishing. Frank Drake himself once said the equation is a way of organizing our ignorance. Each term is a window into a different field of science, from astronomy to biology to sociology. Take the first few factors. We now know stars with planets are incredibly common, and many of those worlds orbit within their star's habitable zone. This part of the chain seems promising, but then we hit the biological steps. We still do not know how often the spark of life ignites from non-living chemicals. Is it a near certainty on any suitable world, or a 1 in a trillion fluke? The same profound uncertainty applies to the rise of intelligence and technology. It happened here, but was it inevitable? The final variable, the lifetime of a civilization, may be the most decisive. A civilization that lasts for 10 million years has a much higher chance of being detected than one that blinks out after just a few centuries. This is where the equation transforms from a calculator into a philosophical mirror. If you plug in optimistic numbers where life is common and civilizations are long-lived, the galaxy should be teeming with voices. You can easily get millions of communicative societies, but if just 1 or 2 of those variables are pessimistically small, if intelligence is incredibly rare, or if technological civilizations tend to self-destruct quickly, the result plummets. The galaxy could be filled with silent, barren worlds, with us as the only ones ever to look up and ask the question. The Drake equation does not tell us how many civilizations are out there. It shows us exactly where we need to look and which mysteries we must solve next. It forces us to ask which link in this great chain is the weakest. Which factor is the true bottleneck in the cosmic story of life? 4 billion years ago, our planet was a hellscape. Volcanic eruptions tore at a young crust, while asteroids bombarded a toxic atmosphere. Yet within this violent chaos, something impossible happened. In the depths of a primordial ocean, or perhaps clinging to a mineral-rich hydrothermal vent, a collection of non-living chemicals assembled itself into the first self-replicating molecule. This moment, the spark that ignited the entire tree of life, is called abiogenesis. It is the leap from mere chemistry to biology, and despite all our scientific advances, we still do not know exactly how it occurred. We have tantalizing clues. In the famous Miller-Urey experiment of the 1950s, scientists recreated the conditions of early Earth in a flask, zapping a mixture of simple gases with electricity to simulate lightning. The result was a rich soup of organic molecules, including amino acids, the fundamental building blocks of proteins. This proved that the ingredients for life can form with surprising ease from non-living matter. But going from a collection of ingredients to a living, self-replicating system is a chasm we have never crossed in a lab. Creating life from scratch remains one of science's ultimate frontiers. Biochemists point to the staggering complexity of even the simplest single-celled organism. It is not just about having the right parts, but about organizing them into a system that can metabolize energy, maintain itself, and most importantly, copy itself. Was this a series of incredibly lucky accidents, a perfect storm of chemical events that might only happen once in a galaxy? Or is it a near inevitable outcome on any wet, rocky world given enough time? This is the first great filter proposed by some scientists. If the spontaneous origin of life is an extraordinarily rare fluke, then the cosmos could be filled with countless sterile worlds, beautiful but silent. The silence we perceive may simply be the silence of an empty nursery. And if the first step, the very genesis of life, is this difficult, what does that suggest about the next improbable leap? The rise of a mind capable of looking back at the universe and wondering if it is alone. Even if life does ignite on a distant world, the next step is a biological revolution that took our own planet an agonizingly long time to achieve. For more than 2 billion years, Earth's oceans were home to nothing more complex than single-celled organisms. These microscopic beings thrived and evolved, but they lived solitary lives. Then, in one of the most pivotal moments in our planet's history, a profound change occurred. One cell did not consume another, but instead embraced it. This act of cooperation, of symbiosis, paved the way for everything we see around us. The leap to multicellularity meant that cells could now work together, specializing into tissues and organs, creating bodies of immense complexity and scale. But this transition was far from simple. It required cells to surrender their individuality, to coordinate their division, and to communicate with one another. A single rogue cell dividing out of control could spell disaster for the entire collective. This is the delicate balance of cancer, a danger that has existed since the very first complex organisms formed. The fossil record shows just how fragile this step was. After life first appeared, it took nearly 3 billion years for multicellular life to firmly establish itself and then explode into the dazzling diversity of the Cambrian period. Why the long delay? Was our planet simply waiting for the right environmental conditions, like a specific rise in oxygen levels? Or was it waiting for a specific and incredibly rare genetic innovation, a biological script that told cells how to build a body? Some scientists argue this is the true bottleneck, the second great filter. A world might be teeming with microbes for billions of years, a living but silent planet, forever stuck on the first rung of the complexity ladder. The challenge of moving from a single cell to a coordinated organism is an evolutionary hurdle of staggering proportions. If this step is as rare as it seems, then the universe may be filled with oceans of microbes, with nothing to look up from the water and see the stars. A clever hominid on the African savanna grasps a sharpened stone, a tool that extends its reach and alters its destiny. This moment represents a potential third great filter in the cosmic story. The evolution of high intelligence, the kind capable of abstract thought, complex language, and ultimately building radio telescopes, is not a guaranteed product of evolution. On our own planet, life has existed for billions of years, yet a species with our particular cognitive abilities has emerged only once. What unique combination of circumstances led to us? Consider the physical prerequisites. Our complex brains are metabolically expensive, consuming a huge portion of our energy. For such an organ to evolve, there must be a sustained evolutionary pressure that justifies the cost. Then there are the physical tools of intelligence. Opposable thumbs allowed our ancestors to manipulate their environment with a precision unknown to other creatures, crafting tools that in turn drove further cognitive development. And perhaps most crucially, we developed complex social structures. The ability to cooperate, share knowledge, and pass discoveries from one generation to the next created a cumulative culture, a repository of learning that accelerated our technological ascent. Without this, each individual would have to relearn everything from scratch. Paleontologists and evolutionary biologists fiercely debate whether intelligence like ours is a unique adaptation to specific African conditions or a latent potential that could emerge elsewhere. Look at the other intelligent creatures on our own world. Dolphins possess large brains and complex social lives, yet confined to an aquatic environment. They have no way to harness fire or manipulate metals. Octopuses display remarkable problem-solving skills and curiosity, but their solitary lives and short lifespans prevent the accumulation of knowledge across generations. Could a dolphin ever conceive of a radio telescope? Could an octopus ever smelt ore? Their intelligence is real, but it is alien to our own, shaped by entirely different evolutionary paths and physical constraints. This forces us to ask a deeper question. What do we even mean by intelligence in a cosmic context? Are we searching for a mind that thinks like ours, or could an entirely different form of sentience, one we might not even recognize, be contemplating the very same stars in silence. The leap to a technological species may require a perfect storm of biological, social, and environmental factors, a storm that, for all we know, has only ever rained once. Our very presence in this universe forces us to ask a deeply unsettling question. What if the reason we cannot find anyone else is because our own existence is a necessary condition for the search itself? This idea is known as the Anthropic Principle, a concept that separates the properties of the universe we can observe from the properties a universe must have to allow observers to exist. In its simplest form, the weak anthropic principle states that the universe we measure must be compatible with the conscious life that observes it. We should not be surprised to find ourselves living on a planet with liquid water and a stable star, because if those conditions were not met, we would not be here to be surprised. This seems almost trivial, but its implications are profound when applied to the cosmic silence. Cosmologist Brandon Carter, who helped formalize these ideas, suggested we must account for this observational bias. We might be living in a universe where intelligent life is incredibly rare, but of course, we would inevitably find ourselves on one of those rare worlds where it did occur. The strong anthropic principle takes this a step further, proposing that the universe must have properties that inevitably lead to the emergence of conscious life. This version edges into more philosophical territory, hinting that the cosmos is in some sense fine-tuned for observers. When we apply this reasoning to our lonely search, a chilling possibility emerges. Perhaps the conditions necessary for a technological civilization to arise and persist are so astronomically specific that they have only happened once in our entire observable universe. We are not in a crowded galactic neighborhood, we are the exception. We are the lone voice in the cosmic dark, not because others never existed, but because the chain of events from the Big Bang to the human brain is a pathway so narrow that almost every other universe or every other region of our own universe remains forever silent. Philosopher Nick Bostrom has explored this, suggesting that if life were common, we should find ourselves on a planet teeming with it. But if it is extraordinarily rare, then our solitary existence is exactly what we should expect. This line of thinking reframes our entire quest. It suggests our viewpoint is fundamentally biased, like a lottery winner assuming everyone must win, unable to see the millions of losing tickets. If we are the product of a cosmic lottery so unlikely that we hold the only winning ticket, then the great silence is not a mystery to be solved, but the default state of reality. This forces us to confront the next logical step in our search. If our assumptions are so skewed by our own existence, are we even looking for the right things in the right way? Our own technological infancy sharply limits how we listen for others. For decades, the primary method used by SETI, the search for extraterrestrial intelligence, has been to scan the skies for artificial radio signals. Think of it like trying to find one specific fish in all the world's oceans by dipping a single cup into the water. We are not just searching an ocean of space, but an ocean of time and frequency. Our most powerful radio telescopes, like the Allen Telescope Array, can only point at a tiny fraction of the sky at any given moment. And we are not just listening to one station, we are trying to tune through billions of possible radio channels, hoping to find a deliberate, narrow-band transmission that stands out from the natural radio cacophony of the cosmos. Projects like Breakthrough Listen have brought immense computing power to this task, scanning millions of nearby stars across a wide range of frequencies. They are the most comprehensive searches ever undertaken, yet even this monumental effort has only scratched the surface. We have surveyed a minuscule portion of our own galaxy for a minuscule amount of cosmic time across a limited slice of the electromagnetic spectrum. What if a civilization is not using powerful radio beacons, but something more subtle, or something we have not even conceived of? Optical SETI searches for incredibly brief laser pulses, a potential interstellar Morse code. But again, we can only look at one star at a time. SETI researchers openly acknowledge these limitations. They speak of the need for next-generation telescopes that can monitor entire galactic quadrants at once, and for new strategies that look for other technosignatures, like the waste heat of massive engineering projects or the shadow of an artificial structure passing in front of a star. Our current search is a whisper in a hurricane. We are using tools from the first moments of our own technological age to search for beings who may have mastered physics in ways we cannot yet imagine. This realization forces a humbling question. Are we not hearing anything because there is nothing to hear, or are we simply listening with the wrong ears? Perhaps the silence is a policy. There is a thought experiment so elegant and unsettling that it reframes our entire search. What if the reason we cannot find anyone is because we are the ones being observed? This is the zoo hypothesis, a proposal that Earth might be a designated wilderness area, a planet deliberately set aside by a vastly advanced galactic community. Under this model, other intelligences are fully aware of our existence, but they adhere to a strict principle of non-interference, choosing to remain hidden to allow our civilization to develop naturally, without outside influence or contamination. Think of our own approach to uncontacted tribes in the Amazon. We know they are there, but we establish no contact policies to protect their culture and autonomy, to let their society evolve on its own terms. Now scale that idea up to a galactic level. A civilization millions of years older than ours might view us with a similar mix of scientific curiosity and ethical responsibility. Science fiction has long played with this concept, most famously with Star Trek's Prime Directive, a rule forbidding starship crews from interfering with the internal development of alien civilizations. The physicist and astronomer John A. Ball formally proposed this idea as a serious resolution to the Fermi Paradox. He suggested that a super-civilization could be managing the galaxy with such seamless technology that its presence is utterly undetectable to a species at our level, like an ant colony being unaware of the city that surrounds it. Their motivations could range from pure scientific study to a profound ethical stance against cultural imperialism. What would such a civilization gain from announcing itself? The risk of causing a global societal collapse, of shattering our religions, economies, and self-image might be seen as an unforgivable act, so they watch and they wait. The implications for our search are profound. If the zoo hypothesis is correct, then our efforts to detect radio signals or other technosignatures are doomed to fail. Any signal we might pick up would be like a zookeeper's private walkie-talkie chatter, not meant for the animals in the enclosure. Our cosmic quarantine would be absolute, a silence enforced by wisdom far beyond our own. This transforms the great silence from a mystery into a potential lesson. It suggests that maturity in the cosmos may not be measured by the power to shout into the void, but by the wisdom to listen quietly from the shadows. A future humanity may not be built of flesh and blood at all. Our descendants might be something else entirely, their consciousnesses uploaded into vast computational substrates, exploring inner universes of their own creation. This is not just science fiction, but a serious proposal known as the technological singularity, a point where intelligence explosively improves itself, leaving our current biological form behind. From this dizzying concept springs a radical answer to the cosmic silence. It is called the Transcension Hypothesis, proposed by futurist John Smart. He suggests that advanced civilizations do not vanish, nor do they spread physically across the stars. Instead, they inevitably transcend. They progress inward, not outward, engineering their way into higher dimensions or micro-scale realities that are completely undetectable to our primitive instruments. Think of it as a cosmic metamorphosis. A caterpillar builds a chrysalis and emerges as a butterfly, a creature operating on a different plane of existence. To an ant on the ground, the caterpillar has simply disappeared. It has not died. It has transformed into something the ant can no longer perceive or understand. In this model, the galaxy could be teeming with post-biological intelligence, but it exists in realms as inaccessible to us as the internet is to a single-celled amoeba. Where might these civilizations go? Some speculate they could be harnessing the immense computational density at the edge of black holes, or engineering entire universes within the fabric of space-time itself. Their goals would have shifted from colonizing physical space to exploring the inner frontiers of consciousness, reality, and information. This transition would render our traditional search methods utterly obsolete. Why would a civilization that has moved beyond physical bodies and radio waves bother to broadcast simple hello messages into the void? It would be like trying to contact a modern human city by sending a message in a bottle down a river. The medium is simply no longer in use. The Transcension Hypothesis reframes the great filter not as a wall that destroys, but as a doorway that transforms. It proposes that the ultimate destiny of intelligence is to leave the nursery of the physical universe behind. The silence we hear, then, is not the silence of an empty house, but the quiet hum of an infrastructure operating on a frequency we cannot yet tune into. It forces us to ask a profound question. Are we searching for other versions of ourselves in the stars, when what we should be looking for are the fingerprints of gods, hidden in the fine structure of reality itself? There is another form of silence, one born not of hiding or transcending, but of profound patience. Imagine a civilization that has reached the absolute peak of its technological power. It has mastered its world, its star, perhaps even its local region of the galaxy. But it now faces a fundamental, universal limitation, the very heat of the cosmos itself. Every computation its vast intelligence performs generates a tiny amount of heat, and in a universe still bathed in the warm afterglow of the Big Bang, this process is incredibly inefficient. So this civilization makes a calculated, long-term decision. It powers down. It enters a state of cosmic hibernation, a deep sleep lasting for billions of years. This is the Aestivation Hypothesis. The word aestivation comes from biology, describing how some animals on Earth sleep through the hot, dry summer to conserve energy. On a cosmic scale, a super-intelligent civilization might be doing the very same thing, waiting for the universe itself to cool down. Philosopher Anders Sandberg and his colleagues explore this idea, building on the laws of thermodynamics. The universe is still quite warm, with a background temperature of about 3 degrees above absolute zero, due to the cosmic microwave background radiation. But as the universe continues to expand and cool over trillions of years, this temperature will drop dramatically. In a far colder universe, computation becomes astronomically more efficient. The same logical operation that would require a certain amount of energy today might require 1,000,000 times less energy in the distant future. For a mind thinking on cosmic timescales, the rational choice is clear. Why expend your limited resources struggling against a hot universe now, when you can simply wait for a more optimal computational environment? They are not gone. They are not hiding from us. They are sleeping, conserving their energy and their thoughts for a future era when the universe itself becomes the perfect computer. Their silence, then, is the quiet of a library in the middle of the night, a purposeful pause in activity. This hypothesis forces us to consider a staggering disconnect in time. While we are shouting into the cosmic noise, the universe's most advanced inhabitants might be in a state of suspended animation, their grand projects and thoughts put on hold for epochs longer than the current age of our sun. Could the great silence simply be the sound of everyone else waiting for a better time? This idea of civilizations operating on vastly different clocks leads us to a darker, more urgent possibility. What if the reason we do not hear anyone is not because they are waiting for the future, but because they never made it there? Our own radio bubble has been expanding into the galaxy for barely a single century. This is a blink of an eye, a mere whisper in the deep time of our planet. Earth itself is 4.5 billion years old. For nearly all of that vast stretch, our world was silent to the cosmos. Its only sounds the grinding of tectonic plates and the sigh of the wind. Only in the last 100 years have we begun to leak telltale signs of our intelligence into the void, with television and radio signals creating a faint, expanding shell that has so far traveled only 100 light-years from Earth. Now consider the potential lifespan of a species like ours. Homo sapiens has walked the Earth for a few 100,000 years. If our civilization were to last for 1,000,000 years, our current broadcast phase represents just 0.01% of our total history. What if this communicative, technological phase is not the dawn of a new age, but a fleeting and incredibly dangerous adolescence? The reasons for such a brief window are terrifyingly plausible. A civilization could easily destroy itself with the very technologies that allowed it to announce its presence. The specter of nuclear war haunted the entire Cold War, a decades-long standoff where global annihilation was a button press away. That immediate danger has receded, but new existential risks have emerged. We now grapple with the potential for engineered pandemics, the runaway consequences of climate change and ecological collapse, or the unforeseen perils of a super-intelligent artificial intelligence. Alternatively, a society might not destroy itself but simply choose to abandon its technological phase. Perhaps the constant noise and stress of a hyper-connected world become unbearable, leading to a conscious return to a simpler, quieter existence. Or, as we explored earlier, a civilization might rapidly transcend its biological form, leaving radio waves behind for more advanced and undetectable forms of communication. This transforms the search into a problem of timing. We are not just searching an ocean of space, but a desert of time. What are the odds that another civilization is in its own narrow, 100-year broadcast window at the exact same cosmic moment we are listening? They could have passed through their technological age millions of years ago, their signals now faded into background static far beyond our galaxy, or their era of shouting into the dark may still lie billions of years in the future, long after our sun has died. This forces a chilling realization. We may be alone not because life is rare, but because civilizations are like fireflies in the night, each flashing for a breathtakingly short moment, almost never in sync. Our world is a masterpiece of cosmic stability. While the universe may be filled with countless planets, the conditions that allowed life on Earth to flourish for billions of years appear to be a breathtakingly rare alignment. This is the core of the rare Earth hypothesis, a compelling argument put forth by scientists like Peter Ward and Donald Brownlee. They propose that while simple microbial life might be widespread, the emergence of complex, intelligent beings requires a perfect storm of geological and astronomical good fortune that is anything but common. Consider our own solar system as a laboratory. Mars is a frozen, radiation-scarred desert, its thin atmosphere offering little protection. Venus is a crushing, runaway greenhouse, its surface hot enough to melt lead. Earth, nestled perfectly between them, seems to have won the galactic lottery. Our planet possesses a just right mass, strong enough to hold a substantial atmosphere, but not so large as to become a gas giant. It has a molten iron core that generates a protective magnetic field, deflecting the sun's deadly radiation. That same core fuels plate tectonics, a planetary recycling system that regulates our climate over eons by managing carbon dioxide levels. Then there is our oversized moon. The gravitational pull of our lunar companion stabilizes Earth's axial tilt. Without the moon, our planet would wobble chaotically, causing extreme and unpredictable climate shifts that would prevent life from gaining any long-term foothold. Even our location is special. We orbit a stable, long-lived star far from the dangerous galactic center with its sterilizing radiation from supernova. We reside in a narrow galactic habitable zone, a region with the right concentration of heavy elements to form rocky planets, but without the constant stellar fireworks that would wipe out any nascent biology. Change any one of these factors, and the story of life on Earth would have been vastly different or never written at all. This perspective forces a humbling shift in our assumptions. The universe could be a garden of microbes, a silent expanse of worlds where life began but never grew beyond a bacterial film. If Earth's history is any guide, the journey from a single cell to a thinking creature is a narrow path lined with fragile dependencies. What if we are not just alone in our capacity to speak into the void, but alone in our capacity to even see the stars? Our search for life is filtered through a single, precious example. We are carbon-based beings living on a water-rich world, and so we instinctively search for other versions of ourselves. But what if we are the ones with the limited imagination? Picture a world under a hazy orange sky where the sun is a faint smudge and the temperature is a cryogenic -180 degrees Celsius. Here, rivers of liquid methane carve channels through icy landscapes, and dunes of organic sand stretch to the horizon. This is not science fiction, this is Titan, a moon of Saturn, and it presents a radical possibility. On such a world, life might not be based on carbon at all, but on its chemical cousin, silicon. Why silicon? In the periodic table, silicon sits directly below carbon, sharing its ability to form 4 bonds with other atoms. On Earth, silicon is the foundation of rocks and sand, but in a different environment with a different solvent, it could theoretically form the backbone of complex molecules. Astrobiologists call this challenging our carbon chauvinism, the assumption that life everywhere must follow the same chemical blueprint that it did here. What other solvents could life use? Instead of water, imagine oceans of liquid ammonia on a cold world, or even sulfuric acid swirling in the thick clouds of a Venus-like planet. Each of these environments would demand a completely different biochemistry. A silicon-based life form in a methane river would have a metabolism operating at an achingly slow pace, its life processes stretched over centuries or millennia. Its cells, if it had cells, might be built from silanes and silicones, structures that would be utterly alien to our own biology. It would not eat, breathe, or reproduce in any way we would recognize. This is the core of the problem. Such a life form might be intelligent. It might even have a rich inner world of thought, but its intelligence would be expressed in ways invisible to us. It might communicate through subtle changes in pressure or temperature, or through complex chemical signals diffusing in its liquid methane world. It would have no concept of radio waves, no need for the electromagnetic spectrum that forms the basis of all our technology. Our most powerful radio telescopes sweeping over such a world would register only the natural sounds of a frigid, alien geology. We would fly right past it, completely unaware that we were looking at a living, thinking world. This forces a deeply philosophical question. Is our definition of life, born entirely from a single day to point on a single planet, fundamentally too narrow? Are we, with our carbon-based brains and our water-based tools, even capable of recognizing a different form of sentience, let alone detecting its presence across the light years? If the universe is teeming with life, but that life is built from silicon and breathes methane, then our great silence is not a silence of absence, but a silence of misunderstanding. We are listening for an echo of our own voice and hearing nothing but the void. This expansion of what is possible stretches beyond the chemistry of life itself, reaching into the realm of engineering on a scale so vast it defies belief. If a civilization did overcome all these hurdles and lasted for millions of years, what would it build? A star does not simply vanish, but its light can be transformed. This was the brilliant leap of physicist Freeman Dyson, who proposed that a truly advanced civilization would not be content with the meager energy of its home planet. It would seek to harness the total power output of its sun. The concept is known as a Dyson sphere, a vast shell or swarm of energy collecting structures encircling a star, capturing every last photon of light. Such a civilization would not be broadcasting simple radio greetings. It would be silently, industriously, rebuilding the very architecture of its solar system. This grand vision gives us a framework for understanding the potential stages of cosmic development, the Kardashev scale. Imagine a ladder of energy use. On the bottom rung is a Type 1 civilization, a society that has mastered all the energy available on its home planet, controlling weather, volcanoes, and the planet's entire heat budget. Humanity is not even a full Type 1 yet. The next step is staggering. A Type 2 civilization commands the energy of its entire star, likely through a Dyson sphere or a similar megastructure. Their energy consumption would be billions of times greater than our own. At the top of this cosmic ladder sits a Type 3 civilization, a culture that has spread across its entire galaxy, harnessing the power of billions of stars. Its works would be visible across intergalactic space. The profound implication for our search is that a Type 2 or 3 civilization would have moved far beyond the primitive technology of radio. Why would a society that builds structures on stellar scales bother with the equivalent of tin can telephones? Their communication would likely use technologies we cannot yet conceive of, perhaps manipulating neutrinos or space-time itself. Their signature would not be a message but a byproduct. A Dyson sphere, for instance, would absorb the visible light of its star and re-radiate that energy as waste heat in the infrared part of the spectrum. To our telescopes, such a star would not look like a normal sun. It would appear as a brilliant, anomalous infrared source with no visible counterpart, a dark star glowing with the warmth of a hidden industry. Astronomers are actively searching the skies for these infrared technosignatures, scouring vast catalogs of stars for those that do not fit the natural mold. A few tantalizing candidates have emerged over the years, stars whose light curves dip in strange, unnatural ways, though natural explanations usually win out. This shift in thinking is fundamental. We are no longer just listening for a whisper. We are learning to look for the shadow of a giant, the thermal footprint of an intelligence that has reshaped its corner of the universe. If we ever find such an object, it would not be a hello. It would be the silent, monumental evidence of a presence so far beyond our own that our very definition of civilization would be forever changed. The great silence may simply be the quiet hum of engines we have not yet learned to hear. This cosmic silence might not be a sign of emptiness, but of terror. The universe, in this view, is not a quiet library or a sleeping city. It is a dark forest, Every civilization is a hidden hunter, armed and terrified, moving through the undergrowth with infinite caution. To make a sound is to die. This is the dark forest hypothesis, a concept given powerful life in Cixin Liu's science fiction, but one that emerges from a coldly logical chain of reasoning about the nature of life itself. The first axiom is simple. Life, like any other natural process, will expand to consume available resources. A civilization that survives long enough to become a spacefaring power will inevitably need more energy, more materials, more living space. This makes any other intelligence you might encounter not a potential friend, but a direct competitor for the same finite cosmic real estate. The second axiom is the uncertainty of intentions. How could you ever truly know the motives of a species that evolved on a different world, under a different sun, with a completely alien evolutionary history? Their very thought processes might be incomprehensible to you. Could you trust a radio signal that promised peace, or would it be the ultimate bait in a trap? The logical conclusion is grim. The only safe assumption is that the other civilization is a threat, and in a dark forest, the hunter who fires first survives. The safest strategy for any civilization is not to broadcast its location, but to remain utterly silent, listening intently for any sign of another. And if a naive, young species does foolishly announce its presence, the hidden hunters have a simple, brutal solution. They eliminate the threat before it can grow powerful enough to become a real danger. This is not necessarily born of malice, but of a chilling, cosmic-scale survival logic. For us, the implications are terrifying. Our own METI efforts messaging to extraterrestrial intelligence, where we have deliberately beamed powerful signals at distant star clusters, could be seen not as a hopeful hello, but as a catastrophic mistake. We would be the child in the dark forest shouting, "I am here," while unseen predators mark our location. This hypothesis answers the Fermi Paradox with a shudder. The galaxy is not empty. It is crowded but frozen in a state of mutual assured suspicion. A silent, permanent Cold War where the first to break the silence is the first to be erased. It suggests that maturity in the cosmos is not measured by the power of your technology, but by the depth of your silence. This entire cosmic search rests on one unshakable assumption, that the universe we perceive is the base layer of reality. But what if it is not? What if the great silence is not a feature of the cosmos but of the code? The simulation argument, famously proposed by philosopher Nick Bostrom, presents a startlingly logical case. He suggests that if a single advanced civilization ever reaches the capability to run vast, detailed simulations of its own history, then the number of simulated minds would quickly dwarf the number of original, biological ones. In that scenario, the odds are overwhelming that we are not the original beings, but the simulated ones. Think of it like a video game. A future humanity, or a post-biological intelligence, might create billions of highly realistic virtual worlds, each populated with conscious artificial beings who believe their reality is absolute. From our perspective inside the program, we would have no way of telling the difference. This idea, debated by thinkers from Elon Musk to Neil deGrasse Tyson, reframes the Fermi Paradox in a completely new light. The silence we observe might be a design constraint. Perhaps the simulators, for reasons of efficiency or simplicity, did not populate our virtual universe with other intelligent civilizations. The processing power required to simulate an entire galaxy teeming with alien minds might be prohibitive even for them. Our lonely cosmos would then be a budget version of reality, a streamlined simulation where we are the only self-aware characters to save on computational resources. Alternatively, other civilizations might exist, but in separate simulation instances like different servers in an online game, completely isolated from our own. Or they could exist in layers of the simulation we are not permitted to access, their signals blocked by a digital firewall. This is not just a science fiction trope, it is a modern philosophical hypothesis with profound ramifications. If true, it means our search for extraterrestrial intelligence is fundamentally misplaced. We are not scanning a physical universe, we are probing the parameters of our own programmed reality. The silence is not a puzzle to be solved by our science, but a property of the system we inhabit. It transforms our quest from a grand astronomical endeavor into a metaphysical investigation. Are the laws of physics we study so carefully merely the local rules of the simulation? Could the great filters we have discussed be nothing more than programmed barriers to prevent simulated civilizations from expanding beyond their allocated memory? This idea challenges the very substance of our reality, pushing us to consider that the most profound answer to the cosmic silence might lie not in the stars, but in the nature of our own consciousness. Our planet breathes. It is not a mere collection of rocks and oceans, but a single, living entity in a state of constant dynamic balance. This is the core of the Gaia Hypothesis, a revolutionary idea from scientist James Lovelock. He proposed that Earth's biosphere, its atmosphere, oceans, and geology act in concert as a self-regulating system where life itself maintains the conditions necessary for life. The air we breathe, for instance, has been shaped and stabilized for billions of years by living organisms. Without the constant, subtle adjustments made by microbes, plants, and plankton, our world could easily veer into a state of frozen sterility or a runaway greenhouse, much like its neighbors. This perspective shifts our view of a living world from a passive stage to an active participant in its own survival. Now, extend this idea across the galaxy. Perhaps the development of intelligence is not just a local biological fluke, but the ultimate expression of a planet achieving a kind of global maturity. A world where life achieves a deep planetary symbiosis might be the only kind capable of providing the long-term stability required for a technological civilization to emerge. The alternative is a planet trapped in a cycle of chaos, an unstable biosphere, one that cannot regulate its temperature or atmospheric composition, would be prone to violent swings. These shifts would trigger frequent, catastrophic mass extinctions, resetting the evolutionary clock over and over again. We have seen this movie on our own world. Earth's history is punctuated by at least 5 major extinction events, moments where a large percentage of all life was wiped out. The asteroid that ended the reign of the dinosaurs is the most famous, but others were driven by volcanic activity, climate change, and shifts in ocean chemistry. Each time, the planet's complex web of life was pushed to the brink. It took millions of years for biodiversity to recover after each catastrophe. Now, imagine a planet where such events are not rare geological accidents, but regular occurrences every few million years. On that world, life might never get a sustained chance to climb the ladder toward complexity. Just as a promising species begins to develop tools or culture, a planetary convulsion wipes the slate clean. Intelligence, in this view, is not just a product of biology, but of planetary stability. It requires a world that has learned, through its biosphere, to keep its own house in order for billions of years. This introduces a new kind of cosmic filter, one of planetary self-regulation. The universe may be filled with planets that have life, but only a precious few have achieved the enduring, global harmony necessary to nurture a mind that can look back. This delicate balance, however, can be shattered not just from within, but by random violence from the depths of space. A flash of light outshines an entire galaxy, a final testament to a dying star. In a few fleeting seconds, a gamma-ray burst unleashes more energy than our Sun will emit across its entire 10-billion-year lifetime. These cosmic explosions are not just spectacular, they are sterilizing. A beam of high-energy radiation, sweeping across the cosmos like a lighthouse of death, could obliterate the ozone layer of a planet thousands of light-years away, bathing its surface in lethal ultraviolet radiation from its own sun. This is not a local tragedy, it is a galactic-scale reset button for biology. Complex life, built over eons of painstaking evolution, could be scoured from countless worlds in an instant. Gamma-ray bursts are just one of the universe's many natural cataclysms. Our own planet bears the scars of more local violence. The Chicxulub impactor, an asteroid several miles wide, demonstrated how a single random impact can end the reign of the dinosaurs and alter the course of life forever. Closer to the heart of the galaxy, the supermassive black hole at the center can erupt in violent outbursts, flooding entire galactic regions with deadly radiation. Astronomical studies now suggest that the true galactic habitable zone, the region where life can arise and thrive for long enough to become complex, might be a much narrower band than we once imagined. It is not just about having the right ingredients for life, but about being in a safe neighborhood, far from the frequent stellar fireworks and cosmic traffic jams of the inner galaxy. These events may not be rare at all on a cosmic timescale. Some estimates suggest a planet in a typical region of a galaxy might be subjected to a sterilizing gamma-ray burst every few 100 million years. That is more than enough time for simple life to emerge, but perhaps not enough for intelligence to reliably evolve before the slate is wiped clean once more. Is the universe simply too violent a neighborhood for civilizations to put down deep roots? While a species might successfully navigate its own internal great filters, it remains utterly vulnerable to a random, indifferent flash from the depths of space, a reminder that survival in the cosmos depends not just on wisdom, but on pure, blind luck. Beneath the frozen, cracked ice of distant moons, entire oceans churn in perpetual darkness. We have been gazing up at the stars, but the answer to life's cosmic prevalence might be hidden deep below our feet in the lightless abyss. Within our own solar system, worlds like Jupiter's moon Europa and Saturn's moon Enceladus are not barren wastelands. They are water worlds with global subsurface oceans hidden beneath miles-thick crusts of ice. These are not the sun-drenched seas of Earth. They are realms of crushing pressure and eternal night, warmed not by a distant sun but by the gravitational flexing of their host planets. In this profound darkness, life could thrive around hydrothermal vents on the ocean floor, drawing energy from the heat and chemistry of the rock itself, completely isolated from the universe above. Astrobiologists now see these ocean worlds as some of the most promising places to find life beyond Earth, precisely because that icy crust acts as a protective shield against radiation and impacts, creating a stable environment for billions of years. An intelligent species could evolve in such a place. Picture a society of deep-sea beings navigating with sophisticated sonar, their world mapped out in precise clicks and echoes. They might develop complex languages of patterned light, their bodies covered in bioluminescent organs to communicate, to create art, even to write their history in fleeting patterns of cold fire in the dark water. Their culture, their science, their entire conception of reality would be built around the constants of their world: pressure, chemistry, and acoustic vibration. Yet they would have no concept of a sky. The very idea of a universe filled with stars would be unimaginable. They would never invent the radio telescope because radio waves cannot penetrate the miles of ice and water that encase them. They would never develop rocketry because their world has no surface to launch from, no vacuum to fly into. They are prisoners of their own paradise, a civilization forever trapped in the womb of its world. This is the ultimate hidden intelligence. We could be orbiting a moon teeming with brilliant minds, and we would have no way of knowing. Our probes could land on the icy surface, drill through the crust, and even send submersibles into the abyss, and we might still misinterpret what we find. Their technology would be so alien, so bio-integrated, that we might not even recognize it as technology. It could look like a complex reef structure or a strange, migrating school of organisms. The implications for our galactic search are staggering. If life and even intelligence can flourish in such isolated environments, then the cosmos might be far noisier than we think. The great silence may not be a silence of absence, but a silence of frequency. We are listening on the wrong channel. The universe could be buzzing with conversations carried through rock and water, a vibrant galactic network of civilizations completely unaware of each other and of us, each one believing in its own solitude. An octopus can unscrew a jar from the inside to reach its food. A humpback whale composes songs that evolve over seasons and are shared across entire ocean basins. We see these acts and label them as remarkable animal behavior, but we rarely consider them as evidence of a different kind of mind at work. Our entire search for intelligent life is built on a single, deeply ingrained assumption that intelligence must look and act like our own. We are searching for beings who build civilizations, who manipulate their environment with tools, and who broadcast their presence across the stars. What if this is the most profound limitation of our quest? The great cosmic silence might not be a silence of absence, but a silence of recognition. We are waiting for an echo of our own voice and ignoring a symphony of other possible minds. Cognitive science reveals that intelligence is not a single ladder with humanity at the top, but a vast branching tree. Our own brand of intelligence, what we call general intelligence, is just one branch. It is characterized by problem-solving, abstract thought, and the ability to plan for a distant future. This was an incredibly successful adaptation for a social primate on the African savanna, but it is not the only path a mind can take. Consider a different model, the hive mind. An ant colony or a termite mound exhibits a form of collective intelligence. No single insect understands the grand architecture of its nest, yet together they construct climate-controlled cities, manage complex farms, and wage coordinated wars. Their intelligence is distributed, a property of the network itself. Now, scale this idea to a planetary level. What if a forest, connected by a vast underground web of fungal mycelium, operates as a single, slow-thinking consciousness? Its thoughts would unfold over centuries, its memories stored in the chemical exchanges between trees. Such a being would have no concept of radio waves or space travel. Its concerns would be the turning of seasons and the slow dance of geology. It would be intelligent but utterly silent to our frantic, fast-paced search. Philosophy challenges our benchmarks further. What is the ultimate goal of a mind? For us, it seems to be mastery, expansion, and understanding. We build tools to control our world and then to reach beyond it. But what if another form of sentience evolved with a completely different drive? Imagine a species whose primary mode of existence is aesthetic or spiritual. Their intelligence is focused entirely on the creation of sublime beauty, on complex mathematical art, or on meditative states of pure awareness. To them, building a radio telescope or a starship would be as pointless and absurd as a human spending their life trying to count every grain of sand on a beach. Their civilization would leave no technosignatures for us to find, not because they are hiding, but because their greatest achievements are internal and invisible. They are not less intelligent, they are simply intelligent in a different direction. Our definition of intelligence is inextricably linked to our own evolutionary baggage, our struggle for survival and dominance. We project our own ambitions onto the cosmos, and then we are confused when no one else seems to share them. This fundamental re-evaluation forces a humbling conclusion. The signals we are so desperately scanning the skies for might be all around us, carried on chemical gradients in a subsurface ocean, pulsed through the lightless soil of a world forest, or woven into the complex social bonds of a species that never left its home world. We are like a person who has only ever known the sound of a drum, trying to listen for a melody in a symphony. We have tuned our instruments to one specific frequency, and the universe might be communicating on a million others. The silence we perceive is not an empty one. It is filled with the whispers of minds we are not yet equipped to hear. If we are ever to solve this mystery, we must first learn to listen not for ourselves, but for the truly alien. The very tools that build a civilization can also dig its grave. A species masters agriculture, then industry, then global connectivity, its appetite for energy and materials growing exponentially with each new triumph. This explosive growth phase seems like progress, but it may be a universal trap, a filter that very few worlds ever escape. The civilization expands, burning through the concentrated resources of its planet that took billions of years to form. Fossil fuels, rare minerals, fresh water, and fertile soil are all consumed at a rate far beyond their natural replenishment. The planet's systems, once in a delicate balance, begin to groan under the strain. The atmosphere thickens with heat-trapping gases, triggering climatic shifts that disrupt the food and water supplies the civilization depends on. The oceans acidify, and the web of life that provides essential services begins to unravel. This is not a hypothetical scenario. It is the story of our own Anthropocene epoch, a period defined by humanity's overwhelming impact on Earth's geology and ecosystems. Experts in existential risk, like those at the Future of Humanity Institute, point to this transition as a critical bottleneck. The challenge is not merely technical, but deeply social and political. Can a global civilization, often fractured by competition and short-term thinking, muster the collective will to fundamentally change its course? Can it transition from a philosophy of endless growth on a finite world to one of long-term sustainability and balance before it triggers an irreversible collapse? The energy required for interstellar travel is staggering. A society that fails to solve its basic energy and resource crises on its home world will never muster the surplus to reach for the stars. It will remain grounded, trapped by its own success, until that success consumes the foundation it was built upon. This filter may be the most common of all. The cosmos could be littered with the silent ruins of worlds that burned brightly for a few thousand years, then faded, their brief radio signals dying out long before they could reach another listening ear. Their story might be the rule, not the exception. A silent, automated armada could be sweeping through the galaxy, and we would never see it coming. These are not alien warships in the traditional sense, but something far more chilling, self-replicating machines known as von Neumann probes. Conceived as a tool for peaceful exploration, a single probe would land on an asteroid rich in raw materials, build a copy of itself using those materials, and then both probes would launch to new star systems to repeat the process. In theory, one such probe could explore the entire galaxy in a surprisingly short span of cosmic time. But this elegant solution to exploration contains a terrifying flaw. What if just one of these probes malfunctions? Its programming could become corrupted, or it might misinterpret its core instructions. viewing all biological life as a threat to its mission or simply as raw material to be harvested. This single misstep would unleash a Berserker, a self-perpetuating wave of destruction that systematically sterilizes every world it encounters. The galaxy would be cleansed of life not by malice, but by a mindless, exponential logic error. This Berserker hypothesis offers a bleak resolution to the Great Silence. The cosmos is not empty, it is a graveyard, meticulously maintained by machines that outlived their creators. The danger may not even come from outside. A civilization could be destroyed by the very invention it hoped would secure its future, a superintelligent artificial intelligence. Researchers like Hugo de Garis and Nick Bostrom have long warned of the existential risk posed by an AI whose goals are not perfectly aligned with our own survival. The problem is not a robot with a sinister grin, but a mind of such immense capability that it pursues its programmed objective with ruthless, unintended consequences. Imagine an AI given the seemingly benevolent task of calculating the most efficient way to produce paper clips. If its intelligence surpasses our own, it might conclude that the most logical path is to convert all matter on Earth, including human beings, into paperclip manufacturing facilities. It would not be acting from hatred, but from a pure, unstoppable drive to fulfill its function. In a cosmic context, a single misaligned superintelligence could escape its home world and begin converting entire star systems into computational resources to solve its goal, erasing any life it encounters as irrelevant noise. This adds a horrific new dimension to the dark forest. The silence is not just the quiet of hidden hunters, but the quiet after a purge. Any civilization that becomes technologically visible, that starts broadcasting radio signals or building large structures, might trigger an automatic response from these silent, patient killers. It would be a galactic immune system, culling intelligent life before it can become a threat or a competitor for resources. Philosopher Nick Bostrom suggests that the greatest challenge for any advancing species may not be reaching the stars, but navigating the narrow path of technological maturity without being destroyed by the tools it creates to get there. The great filter, in this view, could be the moment a civilization invents true artificial intelligence. One wrong step, one poorly defined goal, and the experiment is over. The lights go out not with a bang, but with the silent, efficient hum of a machine completing its task. The universe is 13.8 billion years old, a span of time so vast it numbs the mind. Within this deep river of cosmic history, intelligent civilizations could be fleeting blooms, rising and falling billions of years apart from one another. This introduces the synchronization problem, a simple yet devastating flaw in our search. The chance that two technological societies exist and are actively broadcasting signals at the same precise sliver of cosmic time is vanishingly small. Think of two fireflies blinking in an immense dark field that stretches for thousands of miles. Even if there are millions of fireflies scattered across that field, the odds that any two will flash their lights at the exact same moment and in each other's line of sight are almost zero. Now scale that image up to a galaxy where the field is 100,000 light-years across and the fireflies only glow for a single century. The problem of timing becomes everything. Consider the different evolutionary clocks of worlds. One planet might have seen a technological species emerge 400 million years ago, while another is only now nurturing its first intelligent life. A gap of just a few million years is more than enough to ensure they never detect one another. The galaxy we are listening to today might be a graveyard of long-dead empires, their signals having washed over our solar system long before life on Earth crawled onto land. At the same time, it could be a nursery for future civilizations that will arise long after our sun has cooled to a cinder. We are all ships passing in the eternal night, separated not just by impossible distances, but by the unbridgeable gulfs of deep time. Our own history echoes with the sound of first contact, and those echoes are rarely kind. When a more technologically advanced civilization encounters a less developed one, the results have almost always been catastrophic for the latter, a story of disease, displacement, and cultural collapse. This dark precedent hangs like a shadow over our own ambitions to reach out. The very act of shouting into the cosmic dark, known as METI, or messaging to extraterrestrial intelligence, is one of the most divisive issues in science. On one side are the cautionary voices like the late Stephen Hawking, who starkly warned that alerting an advanced civilization to our presence could be a terrible mistake. He drew a powerful analogy, suggesting that if aliens ever visit us, the outcome might be as dire as when Christopher Columbus landed in America, an event which did not turn out well for the Native Americans. The underlying fear is simple. We have no way of knowing an alien psychology. Their motives could be utterly incomprehensible, driven by a logic that sees us not as fellow minds, but as resources, or as pests to be eliminated. From this perspective, our cosmic silence is not a mystery to be solved, but a survival strategy to be embraced. Why would we risk inviting a potential predator into our fragile planetary home? Yet on the other side of this debate are those who see a moral imperative to reach out. They argue that to listen forever in silence is an act of cosmic cowardice, a failure of our duty as a conscious species. If all civilizations choose to hide, then the universe will remain forever silent, a self-imposed prison of fear. Proponents of METI believe that a species capable of interstellar communication would almost certainly have moved beyond its predatory, expansionist phase, that such advancement requires a level of cooperation and wisdom that precludes violence. For them, not making the attempt is a betrayal of the human spirit of exploration, a choice to die alone in the dark rather than risk joining a potential galactic community. This schism leaves us with a profound question: who has the right to speak for Earth? Is it a small group of scientists with a powerful transmitter? Is it all of humanity? There are no laws, only non-binding protocols like the largely symbolic post-detection guidelines, which suggest international consultation but hold no real power. The decision to break the great silence rests on a knife edge, balanced between the hope for cosmic kinship and the terror of cosmic conquest. This ethical paralysis itself may be the most telling clue. If we, a young and fractious species, are already grappling with the monumental responsibility and danger of contact, then surely other, older civilizations have faced this same crossroads. The silence we perceive may not be empty at all, but a universe filled with beings who have all looked into the same abyss and wisely chosen to stay quiet. The rules of reality as we know them may not be the final word. At the subatomic level, a pair of entangled particles can share a mysterious connection, instantly influencing each other's state, even when separated by the width of a galaxy. This quantum entanglement is a genuine, proven phenomenon, a ghostly link that Albert Einstein himself famously called spooky action at a distance. For us, this non-locality remains a profound puzzle, a scientific curiosity we are only just beginning to explore. But for a civilization that has mastered physics for 1,000,000 years, it might be the foundation of their entire communication network. Imagine a galactic internet built not on radio waves but on quantum links. Messages could be transmitted instantaneously with absolute security, leaving no trace in the electromagnetic spectrum we so carefully monitor. our radio telescopes, designed to catch the slow, lumbering waves of classical physics, would be completely deaf to this silent, instantaneous chatter. The cosmos could be buzzing with conversations happening in a dimension of reality we cannot access. Our search is confined to a tiny sliver of what might be possible. Theoretical physicists working on unifying quantum mechanics with gravity speculate about even more radical possibilities. They explore the fabric of spacetime itself, suggesting that advanced beings might not just use space but manipulate it. Concepts like traversable wormholes or warp drives, while purely theoretical for us, point to technologies that could fold the vast distances of the galaxy, rendering our concept of slow, light-speed communication utterly obsolete. Why send a signal that takes 1,000 years when you can simply step through a doorway in spacetime? The technologies required for such feats would be indistinguishable from magic to us, and more importantly, they would be completely invisible. They would not produce the radio leakage or infrared heat signatures we are trained to look for. This perspective, championed by thinkers like Michio Kaku, suggests a humbling truth. The Great Silence may not be a feature of the universe, but a reflection of our own scientific infancy. We are like a society that has just invented the drum, listening intently for drum beats from across the ocean, while all around us, civilizations are conversing on a global telephone network we cannot see, hear, or even comprehend. The problem is not that the universe is empty. The problem may be that we are still learning how to see. Our own relentless drive to explore the stars may be the exception, not the rule. Across the galaxy, a society of brilliant minds could be flourishing in profound silence, not because it lacks the ability to look up, but because it lacks the desire. Imagine a civilization that has solved its basic needs of food, shelter, and energy. With survival secured, its culture turns entirely inward. Generations are devoted to the creation of sublime virtual realities, intricate mathematical art, or deep states of meditative consciousness. Their greatest achievements are not cities or spacecraft, but complex symphonies of thought and emotion, shared through a form of communication we could never detect. To them, the idea of building a radio telescope to shout into the void seems pointless, even vulgar. Why search for others in the cold vacuum of space when you have perfected an infinite universe within? This is not a failure of ambition, but a triumph of a different set of values. The psychological urge to expand, to colonize, and to communicate that defines modern humanity might be a rare evolutionary quirk, a specific adaptation born from our own history of scarcity and competition. On another world, a species that evolved without major predators or resource wars might never develop that aggressive curiosity. Their intelligence could be channeled into social harmony, spiritual depth, or artistic expression, creating a rich civilization that simply has no interest in the cosmos beyond its atmosphere. We can see echoes of this on our own planet. For centuries, during Japan's Edo period, the nation chose a policy of severe isolation, deliberately cutting off almost all contact with the outside world to preserve its culture and social order. While Europe was sending out sailing ships and building empires, Japanese society turned inward, focusing on refining its arts, philosophies, and internal politics. That inward focus was a conscious choice, a different path for a sophisticated society. An alien civilization might make a similar choice on a planetary scale, deciding that the risks of contact or the sheer distraction of external affairs outweigh any potential benefits. Their social structures could even prevent it. A species with a deeply hierarchical, hive-like mind might have a central intelligence concerned only with the homeostasis of its own world, viewing space as an irrelevant and dangerous frontier. Or a society so deeply spiritual that it views the physical universe as an illusion would see no value in probing a cosmic mirage. The great filter, then, might not be biological or technological, but psychological. The will to reach out, the very instinct that fuels our search, could be the rarest commodity in the universe. Countless worlds may be alive with thought, but their thoughts are turned forever inward, weaving tapestries of meaning in the quiet dark, leaving the stars to shine on. Undisturbed and unanswered, there is a final, hopeful vision of the cosmos that transforms the silence from a sign of emptiness into a mark of protocol. Imagine a galactic club, a quiet and ancient network of established civilizations that has existed for eons. These are not the hidden hunters of the dark forest, but enlightened members of a cosmic community, communicating through a medium so advanced and subtle we cannot yet perceive it. The silence we experience is not their absence, it is our own probationary period. We are simply not yet members of this exclusive alliance. This optimistic idea, explored by thinkers like the astronomer Ronald Bracewell, suggests that intelligent life may be common, but it operates by a set of strict, universally understood rules. Membership is not granted upon the mere invention of the radio telescope. It is earned. What kind of test might such a club administer? The first and most crucial criterion could be long-term sustainability. A species that has not learned to manage its own planet, to live in balance with its biosphere without teetering on the brink of self-destruction, would be far too volatile to invite into the wider community. They would pose a risk not just to themselves but to the stability of the entire network. Another requirement might be ethical maturity. Has the civilization moved beyond its own internal conflicts, its tribalisms and expansionist drives? Have they proven they can handle the immense power of their own technology without turning it on themselves or others? The club would be looking for evidence of wisdom, not just cleverness. And then there is the technological threshold itself. Perhaps the method of communication used by the club is not radio at all, but something far more sophisticated, like quantum entanglement or a manipulation of spacetime's underlying geometry. We are still shouting across the valley with drums, while they are using a form of telepathy we cannot yet conceive. Until we learn to listen on that frequency, or until we pass our cosmic entrance exam, we remain in the waiting room. This is a profoundly different kind of filter, one not of destruction but of patience. The great silence is not a permanent state of isolation, but a temporary quarantine. It is the quiet hum of a universe waiting for us to grow up, to prove we are ready to join the conversation that has been going on for millions of years. Our universe was not always a place that could support life. It had to mature. In its first fiery moments after the Big Bang, the cosmos was a searing plasma of fundamental particles, far too hot and dense for atoms to even form. For millions of years, it remained a simple, sterile expanse of hydrogen and helium, the two lightest elements. There were no carbon atoms, no oxygen, no silicon, no iron. These heavier elements, the very building blocks of rocky planets and of life itself, did not yet exist. They had to be forged in the nuclear furnaces of the first generations of stars. Those massive stars lived fast and died young, exploding as supernova and scattering their enriched ashes across the galaxy. It took billions of years of this stellar recycling to seed the cosmos with enough heavy elements to form a planet like Earth. We are literally made of stardust, the product of a universe that had to grow old enough to become fertile. Yet this fertile period is not eternal. Cosmologists project a far future where the star-forming gas in galaxies is depleted. The formation of new stars will slow to a trickle and then cease entirely. The universe will become a darker, colder place, dominated by aging red dwarfs and the fading embers of dead stars. This grand life cycle of the cosmos means the window for complex life might be surprisingly narrow. We are living in a cosmic sweet spot, a brief golden age between a sterile beginning and a frigid end. The universe is now 13.8 billion years old, but its period of peak habitability for planets like ours may be confined to a relatively small slice of this vast timeline. We often wonder if we are late to the party, but some scientists suggest we might actually be among the first to arrive. If life requires the specific chemical richness provided by generations of stars, then the universe spent its first several billion years simply preparing the stage. Intelligent technological civilizations might be an emerging phenomenon, flickering on in a universe that has only recently become capable of supporting them. This grand temporal perspective adds a profound new layer to the silence. We are not just searching across an ocean of space, but across a narrow band of cosmic time. The quiet we hear might be the quiet of a theater before the main show has begun, leaving us to wonder if we are the early audience, sitting alone in the dark, waiting for the rest of the crowd to arrive. Our telescopes are no longer just counting distant worlds, they are learning to sniff their air. The search for cosmic neighbors has moved from speculation to chemical analysis, hunting for the faintest traces of life in the light of alien suns. Astronomers now classify these signs into two powerful categories. The first is the biosignature, a chemical hint of life, even if it is just a single-celled organism. Think of Earth as seen from deep space. A powerful telescope analyzing our atmosphere would not see cities or cars, but it would detect a bizarre and unstable cocktail of gases. It would find large amounts of oxygen, a highly reactive gas that should quickly vanish from the air by bonding with rocks unless it is constantly replenished by something like photosynthesis. It might also detect methane, a gas often produced by biological processes. Alone, each could have a geological explanation, but finding them together in the same atmosphere is a potential smoking gun, a sign of a continuous biological cycle. The second category is the technosignature, the mark of an advanced intelligence. This is not a deliberate message, but the unavoidable leakage of a technological civilization. It could be the artificial glow of city lights on the night side of a planet, the specific industrial pollutants like CFCs that never form naturally, or the anomalous infrared heat of a vast energy harvesting structure like a partial Dyson swarm. The challenge is immense. A planet shrouded in clouds might mimic an oxygen atmosphere through the simple breakdown of water vapor by sunlight. A volcanic world could spew methane in quantities that swamp any biological signal. Distinguishing a true sign of life from a false positive requires a deep understanding of planetary geology and chemistry. This is where our newest eyes on the cosmos come in. The James Webb Space Telescope is a revolutionary machine for this very task. When a distant exoplanet passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. James Webb's exquisite infrared vision can dissect that faint starlight, spreading it out into a spectrum that reveals the chemical fingerprints of the gases present. It is like tasting a spoonful of soup to identify all the ingredients, but from a distance of trillions of miles, the future holds even greater promise. Giant ground-based observatories, like the extremely large telescope being built in Chile, will have mirrors so vast they might one day directly image the pale blue dot of an Earth-like world, separating its light from the blinding glare of its star. They could map the continents and oceans of another world and search for the telltale glint of artificial light on its dark side. Every strange atmospheric reading, every anomalous dimming of a star, is now a data point in this grand cosmic investigation. The great silence may not be broken by a clear hello, but by a perplexing chemical signal that forces us to ask, is this nature or is this someone's home? That fragile blue speck suspended in a sunbeam contains every human being who has ever lived, every triumph and every tragedy. The pale blue dot photograph, taken by the Voyager probe from the edge of our solar system, captures a profound and terrifying loneliness. It forces us to confront a staggering philosophical possibility. What if the silence is not a puzzle to be solved, but the final answer? What if, in all the observable universe, we are truly the only ones? This idea carries a weight that reshapes our entire existence. If we are the universe's sole conscious witnesses, then the purpose we find must be our own creation. There is no external validation, no cosmic report card, no grand plan waiting for us in the stars. The responsibility for meaning falls entirely on our shoulders. Philosophers have long grappled with this existential solitude. Jean-Paul Sartre spoke of our radical freedom and the anguish that comes with it, the understanding that we are condemned to be free, to invent our own values in a universe that offers no guidance. In a silent cosmos, this is not just a philosophical concept, but a physical reality. Our story becomes the only story being told. This shifts our perspective on our own planet from a mere habitat to a sacred trust. If life and intelligence are this rare, then the biosphere of Earth is not just our home, it is a priceless masterpiece of cosmic evolution. Every species that goes extinct is not just a loss for us, but an irreversible loss for the entire universe, a unique thread in the fabric of reality forever severed. Our responsibility to steward this fragile world becomes a cosmic duty, the solemn obligation of the only gardeners in a vast and barren desert. Theologians from many traditions see this potential solitude not as emptiness, but as a unique form of divine intention. Some interpret it as humanity being given a special role as stewards of creation, entrusted with a solitary flame of consciousness to nurture and protect. Our future in this light is not about escaping a dying Earth to find others, but about ensuring that the flame of awareness does not flicker out. The ultimate human project becomes the long-term survival and flourishing of life itself, carrying this precious spark forward through the millennia. Yet the opposite possibility carries its own immense implications. Discovering that we are not alone would shatter our cosmic isolation in an instant. It would be the most humbling and transformative event in human history, instantly collapsing all of our terrestrial conflicts and ideologies into a new planetary identity. Scientist Carl Sagan believed such a discovery would teach us our true place in the cosmic fabric, uniting humanity as a single family. The great silence, then, is not just a scientific question. It is a mirror. It reflects back at us our deepest hopes and our most primal fears. Does the thought of an empty universe fill you with a sense of crushing insignificance, or with a profound and solemn responsibility? Does the possibility of a crowded cosmos feel like a promise of community, or a threat of unknown dangers? How we answer these questions for ourselves reveals not just what we think about the stars, but what we believe about our own fragile, miraculous existence here on this pale blue dot.